Hello and welcome to Lesson 5. In the previous lesson, we spent time exploring, or at least reminding ourselves of, ways in which the viscoelastic response of polymers could be measured, as we now know that viscoelasticity has a significant impact on polymer processing operations. We also looked at how the molecular structure and molecular weight distribution affected viscoelasticity, as well as discussing the effect of temperature on viscoelastic parameters. In this part of Lesson 5, we're going to explore some nonlinear viscoelastic constitutive equations that have analytical solutions to key material functions. This allows us to fit fluid models to experimental data relatively easily. But before we do that, let's start by asking a very crucial question. If we've been doing some rheological investigation of some viscoelastic polymers, we probably have data such as this that I'm about to show on the board. We may have, for example, a plot of our two viscoelastic moduli, the elastic modulus, the viscous modulus, G' and G double prime, as a function of angular frequency. We may have even backed out a complex viscosity based on those two moduli. We may even have gone so far as to do some time-temperature superposition to maybe look at either the nonlinear viscoelastic response, for example, it might be manifesting in the apparent viscosity, or it might be manifesting in a first normal stress difference, and then created a master curve of those data as a function of, for example, shifted shear rate. Why? Why are we doing this? These are not short experiments to do. They require expensive equipment. They're time consuming. So there has to be a good reason to do this. And there has to be a good reason to take this data further. So let's have a little look at that before we start digging into the detail of the constitutive equations in their own right. So here on the whiteboard, I've put a blue box. And in that blue box, I've put some arbitrary viscoelastic parameters. The elastic modulus G', the viscous modulus G double prime, maybe my first normal stress coefficient, psi1, maybe a second normal stress coefficient, psi2, and apparent shear viscosity E/0. Okay, fine. So we've gone to some trouble to actually obtain these data. And the rationale for that may well have been to say, well, what we really want is a metric for quality control on our process. We, as a polymer processor, for example, might be having different batches of polymer every week. We have a process that requires stable, steady extrusion. What we want to ensure is that the extrusion properties of the new batch of polymer are essentially the same as those that we're currently processing and that we know that works. We've seen in the last lesson that simple metrics such as the melt flow index only give us a very, very, very small bit of insight into the full nature of the viscoelastic response of a polymer. And so it's perfectly plausible to have a number of different polymers with slightly different architectures with the same melt flow index that won't end up processing in the same way. And so we need more data to actually do that batch to batch to batch quality control to ensure that we've got a stable process. Okay, fine. So we can, to a certain extent, do that operation with the raw rheological data that we can obtain directly from rheometry. Now, sometimes it might be useful to take that one step further, and that's the steps that we're going to develop in this lesson, which is to fit these raw data to a viscoelastic model. Again, that might give you another quality control metric. Rather than comparing, for example, I don't know, the G', G double prime crossover point, or looking at the form of G' as a function of angular frequency and G double prime as an angular frequency, what we might say instead is, well, actually what this infers is that we've got a viscoelastic model that needs three modes to describe these data, and here are the three key relaxation times that that infers. So what we've done is we've condensed a potentially large amount of experimental data maybe into three parameters, relaxation times. What we might also be able to do is to choose an appropriate constitutive model and say, look, fine, okay, we can fit, for example, a 3 or 4 mode Giesekus equation to this linear low density polyethylene. It describes the shear thinning, it describes the normal stress responses, and what it gives us are a couple of parameters that we can now also use to, for example, estimate the amount of die swell, or maybe, for example, to estimate the amount of time taken for stress in an extrude to relax below a certain threshold stress. And that might be pertinent, for example, when we're cooling an extrude, and when the stresses during that cooling process need to relax to a sufficient extent such that when the material that we've extruded is solid, we don't end up with embedded stress in there that over whatever service period that the product that we've made is in, it doesn't cause a lack of tolerance or problems. So we might be able to do some simple process analysis with parameters that we can back out from a simple viscoelastic model. We might take this yet one stage further still. Now, the holy grail of viscoelastic flow modelling has been worked on for upwards of 40 plus years, and all the theory is established. One of the things at the moment that is allowing this to become a lot more tractable is just simply cheap computational power. Viscoelastic flow modelling is a significantly harder computational piece of fluid mechanics than Newtonian flow modelling. And so it needs a lot more compute power, and it also needs well characterized viscoelastic constitutive equations. And so that's another use that we may put rheological data to. So that said, let's now review some viscoelastic models. Let's have a look at some of their features, and let's see what form of analytical solutions that we can find for key parameters such as apparent viscosity as a function of shear rate. So if you think back to EPD650, we talked about viscoelastic constitutive equations. The constitutive equations are equations that link stress to rate of deformation. So there's a few that you should already be familiar with. Hopefully you're familiar with the concept of the Newtonian fluid. It's the simplest constitutive equation in fluid mechanics that we can find. The state of stress, tau, that stress tensor, is equal to one material constant multiplied by the rate of strain tensor, gamma dot. And that one material constant is our Newtonian viscosity. There's no inkling of time memory in this. The state of stress now is directly proportional to the rate of strain now, and the rate of strain is simply a measure of the deformation of the material. So the Newtonian fluid is a nice simple description that we can get a long way with so long as we're not dealing with molten polymers. Now, if we start to include concepts of viscoelasticity, again, if one thinks back to EPD640, we talked in some length about the Maxwell model. And this was effectively a Hookean spring connected to a viscous damper in series. And we looked at what happens when you deform a Maxwell element and what predictions of apparent viscosity that you get. And then again, we spent some time manipulating Maxwell into forms where we could add extra bits of physics to maybe describe nonlinearity and extra bits of physics to describe the real response of materials. And we went from a single mode model to a multi-mode model. So the key problem with Maxwell, in whatever form we take it, be it simple differential, upper convected or integral, is it is a linear viscoelastic model. And that is to say that it will always predict a constant viscosity in steady shear, which we know we don't observe. However, it's a building block to get us to something more realistic because it does feature time memory, which polymers do have. And it does also feature non-zero first normal stress differences, which again polymers will have and no Newtonian fluids won't have. So upper convected Maxwell is a very useful stepping stone, not only to understand how we put together constitutive equations from a phenomenological standpoint, but also then to see how these things like a first normal stress difference manifest once we have that constitutive equation in upper convected form, which I've put there on the board. We spent a little bit of time also looking at a nonlinear viscoelastic constitutive equation written in differential form, and that was the Giesekus constitutive model. And this model, again, which I put on the board there in red, stems effectively from Maxwell. If we look at the first few terms in Giesekus, they're the same as what you find in Maxwell, but crucially, it contains a nonlinearity. And that nonlinearity is quadratic in polymer stress, And what this allows the Giesekus model to do is to predict things such as shear thinning in steady shear, and the presence of a non-zero second normal stress difference. And this is starting to move towards the sorts of features that we see in real materials. Now, the nice thing is that all three of these equations, Newtonian, upper convected Maxwell and Giesekus, have analytical solutions to key material functions, which is great, because if we can back out, for example, an expression of how steady shear viscosity changes as a function of shear rate, we can start to fit experimental data to that model. We may have, for example, 2, maybe 3 adjustable parameters in the model that allow us to change the shape and form of that viscosity curve, and we can do that with an optimization problem to allow us to fit the experimental data. Now, let's take a bit of time out. If any of the concepts that I've been talking about so far feel unfamiliar, or perhaps not quite as fresh as they could be, go and have a look at some of the EPD650 videos on, for example, Maxwell, on convected constitutive equations, and on the Giesekus constitutive equation. Now, I've put the links there on my whiteboard. They'll also be in the description of this video, so please do go and visit those if the material up until this point has felt a little unfamiliar and perhaps a little uncomfortable. Okay, so what I'd like to do now is to introduce to you 3 more nonlinear viscoelastic constitutive models that may be of use to try and fit experimental data such that we can get some parameters that we might be able to describe our polymer with. The first of these models is the White-Metzner model. Now, White-Metzner again starts from upper convected Maxwell and just has one very simple change. And it's a change that we've seen before when we looked at the difference between Newtonian fluids and generalized Newtonian fluids. And that was to allow our steady shear viscosity to vary as a function of shear rate. So let's see how we incorporate that concept within a viscoelastic constitutive equation. So here on the board, I've put the statement of upper convected Maxwell. In the footnotes on the board, I've also put a reminder as to what that first differential stress looks like. So that's my first upper convected derivative of stress. And I've also put a reminder on the board what the magnitude of my shear rate is with respect to the shear rate tensors. Okay, so what we do with upper convected Maxwell is look at the term that multiplies that first upper convected derivative. It's just simply the relaxation time, lambda. That relaxation time we can express as a measure of viscosity divided by a material modulus. It's eta naught over g. And that is where we can manipulate what eta naught is with respect to shear rate. And so we simply say that eta naught now can vary with shear rate, both on the left-hand side of the equation, in that term that was wrapped up in the relaxation time, there in pink, and also on the right-hand side of the equation, where eta naught was explicitly stated. Without going into details, I'm going to give some key results now for you. So the steady shear viscosity for the White-Metzner model is whatever we've chosen for our variation of viscosity as a function of shear rate. It could be power law, it could be Corot, it could be Corot-Yasuda, it could be A-ring, it could be a number of different things. Now, we also get a first normal stress coefficient that looks kind of Maxwellian, but again with variation of that viscosity term. We also get a second normal stress coefficient equal to 0. We can also derive what the steady extensional viscosity should look like, and I've put that expression there on the board for you as well. And one of the things that we'll say later on, but I'll mention now, is that when we're fitting viscoelastic constitutive models, it's a good idea to be able to fit both the steady shear parameters and the extensional parameters together. If one model can describe both of those, typically that model is going to be pretty representative of how that polymer is behaving. Let me introduce another nonlinear viscoelastic model now, the Oldroyd 4 constant. Now, in White-Metzner, what we did was kind of cheat a bit. We said, well, we don't really want a prediction of a constant viscosity as a function of steady shear rate because we know that doesn't happen in real materials, and so we'll just fit a a generalized Newtonian model to that steady shear. We might fit a Corot. What the two constitutive models I'm now going to show you do, they formulate their equations in such a way such that shear thinning is a natural part of the formulation rather than being kind of a bolt-on. So the Oldroyd 4 constant model is a simpler version of the Oldroyd 8 constant model, and it's written as shown there on the board. So we can see a couple of things automatically. On the left-hand side, we've got one or two terms that look a little bit like upper convected Maxwell. We've got that lambda 1 tau 1 term, and we've got plus tau. On the right-hand side, we also have that eta naught gamma dot term. We've also got two other terms, one of which involves the trace of tau, and the other of which involves the second upper convected derivative of the strain. So let me expand those two new terms out for you. Now, the trace of a tensor is simply the sum of the diagonal components. So trace of tau is tau 1, 1 plus tau 2, 2 plus tau 3, 3. The second upper convected derivative of strain I've put there on the board for you and can be written in terms of the rate of strain. And that is where the nonlinearity comes from in this particular constitutive model, or one of the places it comes from. Again, going to some key results. Our steady shear viscosity now naturally varies with shear rate according to the values of the relaxation times lambda 1, lambda 2 and lambda 5. We also have non-zero first and second normal stress coefficients, and they vary with those relaxation times as shown there on the board. We can also get an analytical equation that describes the steady extensional viscosity as well. And we can see if we take the ratio of eta E divided by eta 0, and if all lambdas are 0, we end up with 3, which is our Troughton ratio for a Newtonian fluid. As soon as we start to put in values that are non-zero for these relaxation times, we diverge away from that Newtonian Troughton ratio result. Okay, so that's Oldroyd 4 constant. There's one other equation that I would like to mention, since it has a good deal of attention devoted to it in the literature, and that is the model due to Phan-Thien and Tanner. And if we have a look at the form of that constitutive model, again we can see elements there that look somewhat Maxwellian, but we're now starting to diverge quite a good deal away from that. We've got lambda multiplied by the first upper convected derivative of the stress tensor, lambda tau brackets 1, on the left-hand side, and on the right-hand side we have eta naught gamma dot. The remaining two terms in Phan-Thien and Tanner, or PTT, don't look particularly Maxwellian at all. So let's have a little look at what they are. So again, trace of tau is simply tau 1, 1 plus tau 2, 2 plus tau 3, 3 is the sum of the diagonals on the tensor. And the key thing here not to get confused about is z trace tau is simply saying z is a function of trace tau. This is not z multiplied by trace tau in brackets, as could be very easily interpreted from the way it's written here. And I've written it here purposely in that manner because that's the way it's represented in the literature. And so I wanted to put that on the board now to highlight this potential ambiguity and to make sure that we're using this in the right way. So z trace tau is simply a function of trace of tau, and it can take one of two forms. It can take an exponential form, or it can take a linear form. And the particularly eagle-eyed of those amongst you will see that the linear form there is just simply a binomial expansion of the first two terms of the exponential. And so at small values of the bracket inside the exponential, they're effectively the same thing. So let's jump to some key results for this. Again, we can get an analytical solution for the steady shear flow viscosity. And again, it's a natural function of the constitutive equation. We haven't force-fitted any generalized Newtonian model to it. And again, we can see that if the various parameters that describe shear in Phan-Thien and Tanner, we'll be talking more about this in the next part of this lesson, are set to 0. So if C there is set to 0, we simply get that eta equals eta 0. And if we see what that means in the constitutive equation, it basically means we're reverting back to something quite Maxwellian. PTT also gives us non-zero first and second normal stress coefficients, and as I've put there on the board. So again, these can be fitted to experimental measurements of these data. The key difference with PTT is that there isn't an analytical solution for the steady extensional viscosity. One can write down the equations that govern the steady extensional viscosity, but then they have to be solved numerically. And this is what you find very often with more complex constitutive equations, is that we can write out the various forms of the equations that we need to, for example, fit viscosity to experimental data, but there isn't an analytical solution to them. So we're back into a numerical optimization exercise. And we're going to be talking about both of those problems later on in this lesson. So we haven't yet mentioned anything about G prime and G double prime, and these are data that we get relatively readily and relatively quickly from dynamic rheometry. So let me just highlight a few results for you here. The White-Metzner result is the same as the Maxwellian result. What we find with Oldroyd 4 constant is that the various values of the relaxation times also now start to affect the values of the elastic modulus, G prime, and the viscous modulus, G double prime. And in respect to Giesekus, which is sort of assumed knowledge, but you won't have come across the expressions for G prime and G double prime before, again we can see the formulation of Giesekus will revert to Maxwellian, and we can see if we put lambda 2 equal to 0, that's the result we get. But the presence of having lambda 2 there will give us a slightly different result. And so what we can always do is just quickly check in our own mind that a parameter, in this case G prime and G double prime, reverts back to what we expect so long as we set various parameters in there to known quantities, in this case to 0. Right, so we've got a whole menu now of viscoelastic constitutive equations. What do we use them for? When do we use them? Okay, so what we're aiming for is to try and fit both shear and extensional experimental data with one constitutive equation. We may require several modes to be used, but we should be able to get some reasonable representation of behaviour with the one model in order for that model to be deemed successful. Now, the Oldroyd 4 constant model predicts effectively an infinite extensional viscosity at large extension rate. So if we're dealing with flows that have very strong elongational components, it's probably best to avoid that particular model. When we're fitting PTT, as we'll see in the next part of this lesson, we've got to be aware that C is the parameter that dominates shear flow, and epsilon is a parameter that dominates elongational flow. And so you're going to have a full data set of both shear and extension to fit PTT completely anyway. What we find is in our choice of Z for PTT is that the exponential form can cause a turning point in extensional viscosity. Now, whether that impacts what we're trying to do or not is a matter of what we're attempting to do. Remember, all along I've been saying that it's important to understand the problem you're trying to solve, and also then to appreciate the level of accuracy of solution that you need. If an exponential form of Z for PTT works well for the problem you're trying to solve and isn't misleading in any of the ways it gives you an answer, probably not a bad thing to use. However, we need to be aware of model limitations. So what I would like to do in the remaining parts of this lesson is outline a few things. I want to spend some time looking at backing out the expressions that we've just seen. We've got a constitutive equation. Okay, we're taking at face value that this is the form of the steady shear viscosity prediction for it. How do we get there? That's what we're going to do next. Then what we're going to do after that is to say, well, we've got it. You said fit it to experimental data, but how do we fit it to experimental data? That's what we'll address in the final part of this lesson. So let's recap a few key points. Firstly, viscoelastic data is very important to have to understand how a polymer behaves and to get some insight into how it might behave in a given process, and also therefore to give you a metric of quality control. Sometimes being able to describe viscoelastic data by an appropriately chosen nonlinear constitutive equation gives you more to work with. It can pave the way for maybe a better quality control, because we might say, okay, we're aiming for this relaxation time. Yep, that gives us this relaxation time. We might be doing some flow analysis with those data. How quickly does stress decay? We might even be going whole hog and going to do some flow modelling. So in terms of assumed knowledge, I'm assuming that you know all about upper convected Maxwell and all about Giesekus. If not, please go back and review this material from EPD650. And we've built on these constitutive equations this lesson by also introducing 3 more nonlinear versions. We've got White-Metzner, we've got Oldroyd 4 constant, and we've also got Phan-Thien Tanner.